Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 9 from the course, but make sure you have watched the previous ones before viewing this one. In the last lecture, we started our discussion on the topic photoelectric effect. Today we will carry the discussion further. We would be discussing about a very important term in the effect, that is the stopping potential, and then we would be doing a few numericals based on this concept. So in the last lecture, we discussed about the photoelectric effect where light was allowed to fall on a metal electrode which caused the emission of the photoelectrons. The electrons emitting the electrons is called as the emitter and the one receiving the electrons is called as the collector. Do you remember what was the polarity of the battery? Well, it was such that the emitter is at a negative potential with respect to the collector, and the electrons, they could move from the emitter towards the collector because the electrons, they were negatively charged and the collector positively, right? So, and as the positive difference increased, the photoelectric current increased until the saturation point this was happening. Now what will happen if we add a variable voltage source to the circuit so that the polarity of the battery is reversed? So you can see here that we have reversed the polarity of the battery as you saw in the photoelectric effect diagram. Okay, and now the collector, this is at a negative potential as compared to the emitter. So now what will happen? The electrons, they are negatively charged. They will be repelled by the negative collector. And if we increase the voltage of the variable voltage source, then what will happen? This repulsion between the negatively charged electrons and the negative collector, this is going to increase. And eventually a point will be reached when no electrons will be able to reach the collector. This point of this value of voltage at which no electrons can reach the collector, this is called as the stopping potential. So what is stopping potential? The stopping potential is that retarding potential, right, V naught, when no electron reaches the collector and hence the current stops flowing. So I hope this is clear what is stopping potential. Now, the work done by the stopping potential, this is equal to the maximum kinetic energy of the electrons. So the maximum kinetic of energy of the electrons is what we have stopped by putting a stopping potential. So the work done by this stopping potential would be E into V naught, and how is it so is what you are going to study in physics. I would not be doing that, but please do remember the relation that the work done by the stopping potential, that is the charge multiplied by the potential. So the charge on the electron E and V naught, the stopping potential, this will be equal to the maximum kinetic energy of the electrons. Or we can say that the kinetic energy is directly proportional to the stopping potential. And E, the charge on electron, 1.6 into 10 power minus 19 coulomb. So what would be the value of the stopping potential? V naught is equal to the kinetic energy, half mv square, divided by the charge on the electron, which is 1.6 into 10 power minus 19 coulomb. And why are we studying about the stopping potential? What was the need to study that? Well, we wanted to know the kinetic energy of the photoelectron, but we did not have a way to determine that. So we have determined the maximum kinetic energy of the photoelectron by knowing the value of the stopping potential. So if we know the stopping potential, we know the charge on the electron, we can find out the maximum kinetic energy of the photoelectron, right? So now finally we have a very important relationship, one which was given by the Einstein, and now this of the stopping potential. So half mv square is equal to h into nu minus nu naught, and this is equal to the work done by the stopping potential, that is v naught into E. Okay, so please do remember this. This is very important. And also do remember that when light of threshold frequency, this is incident, then the photoelectrons, they are just coming out. There is going to be no kinetic energy, and hence no stopping potential will be required. So now let us do a few numericals based on the photoelectric effect. The first numerical says that when electromagnetic radiation of wavelength 300 nanometer falls on the surface of sodium, electrons are emitted with a kinetic energy of 1.68 into 10 power 5 joules per mole. What is the minimum energy needed to remove an electron from sodium? What is the maximum wavelength that will cause a photoelectron to be emitted? So we are given the wavelength of the electromagnetic radiation. So that is 300 nanometer, or in the SI notation, this is 300 into 10 power minus 9 meter. So from this we can calculate the energy of the photon using the relation that energy is h nu and nu is c by lambda. So we have the energy of the photon to be hc by lambda, and you are supposed to remember the value of the Planck's constant, which is 6.626 into 10 power minus 34 joules second. The velocity of light 3 into 10 power 8 meter per second, and the wavelength was given to you. So you get the energy of the photon to be 6.626 into 10 power minus 19 joule. The next thing you are given is that the electrons, they are emitted with a kinetic energy of 1.68 into 10 power 5 joule per mole. So this is the kinetic energy for a mole of electrons. And what do you need is for an electron. Okay, so we will convert the kinetic energy into the kinetic energy for one electron. And how would you do that? We would simply divide this kinetic energy by the Avogadro's number. You will get the kinetic energy of the electron to be 2.79 into 10 power minus 19 joules. Now the minimum energy or the binding energy, so that is h nu naught, and this is equal to h nu minus half mv square. So put these values, you will get the answer for the minimum energy required to remove an electron from sodium to be 3.84 into 10 power minus 19 joules. And for the next part, we have to calculate the wavelength. So according to this energy, you can find the wavelength again using the relation E is equal to hc by lambda. So lambda would be hc divided by E, and you are going to put the values and you will get the lambda to be 5.18 into 10 power minus 7 meter, and this is equal to 518 nm. And this is corresponding to the green light. So this wavelength is of the green light. So the next question says that a near UV photon of wavelength 300 nanometer is absorbed by a gas and then emitted as 2 photons. One photon is red with the wavelength 760 nanometer. What would be the wavelength of the second photon? So what we are going to do in the numerical is basically that we have a wavelength 1 photon, and this photon is being emitted as other 2 photons. So the energy of the UV photon has to be equal to the energy of these 2 photons. And if you can appreciate that, that is the Rest part is going to be very easy. So we have the energy associated with the UV photon to be called as E, which is equal to hc by lambda. So we have hc divided by 300 into 10 power minus 9 meter for this wavelength. And then the red photon energy, E1 we are calling it, and that would be also equal to hc divided by 760 into 10 power minus 9 meter. And the wavelength of the other photon which we have to find, that is energy, is E2, and this would be equal to hc by lambda 2. So we have the energy of the UV photon to be equal to the energy of the two photons which it is breaking into. So E is equal to E1 plus E2. And now you have to just put these values in the equation and you will get your result. So this you will calculate and you will find that lambda 2 on solving comes up to 500 nanometer. The third question says that the work function for cesium atom is 1.9 electron volt. Calculate the threshold frequency, the threshold wavelength of the radiation, and if cesium atom is irradiated with a wavelength of 500 nanometer, calculate the kinetic energy and the velocity of the ejected electron. So we have the work function omega naught to be h nu naught, right? The threshold frequency. So from this you can calculate the threshold frequency. So the threshold frequency is going to be the work function divided by the Planck's constant. But here you will see that the energy is in electron volts and the Planck's constant, the unit of the energy in that is joule. So you have to convert the electron volt into joules. So that would be what? 1 electron volt is 1.602 into 10 power minus 19 volt. So the potential of 1 volt and the charge on the electron. So this forms the energy, right? So this is 1.602 into 10 power minus 19. The charge on the electron multiplied by 1 volt. So this becomes 1.602 into 10 power minus 19 joules. So now you can multiply 1.9 into this 1.602 into 10 power minus 19 and divided by the Planck's constant. So you will get the threshold frequency to be 4.59 into 10 power 14 second inverse. And lambda naught is going to be C over the threshold frequency. So this you will calculate and you will get the value to be 654 nanometer. And now we have to calculate the kinetic energy and the velocity of the ejected electron when the radiation falling is of a wavelength 500 nanometer. So the work function h omega naught, so this, right? So this was 1.9 into 1.602 into 10 power minus 19 joules. So this comes up to 3.04 into 10 power minus 19 joules. And then the energy of the incident radiation that you can calculate. So that is going to be h nu, and h nu is hc by lambda. Put the values, you will get this as 3.97 into 10 power minus 19 joules. And for your relation you have h nu is equal to h nu naught plus kinetic energy, and because you need the kinetic energy, so kinetic energy is h nu minus h nu naught. Put the values of both the energies and you will get kinetic energy to be 0.93 into 10 power minus 19 joules. And this kinetic energy is equal to half mv square. So from this you can calculate the velocity of the electron, where kinetic energy you have just now calculated and mass of the electron 9.1 into 10 power minus 31. So we can calculate V from this relation. So calculate V square, then the square root of that, you will get the velocity to be 4.52 into 10 power 5 meter per second. So now one numerical based on the stopping potential. So the numerical says that the ejection of photoelectron from silver metal in the photoelectric effect experiment can be stopped by applying a voltage of 0.35 volt. When the radiation is 256.7 nm, calculate the work function of the silver metal. So we know that the energy of the incident radiation is equal to work function plus the kinetic energy of the photoelectrons. And the energy of the incident radiation, you are now perfect in that, I think, that E is equal to h nu, where nu is c by lambda, so we have h c by lambda. And putting the values, because you are given the wavelength to be 256.7 nm or 256.7 into 10 power minus 9 meter. So put the values over here, you will get the energy of the incident radiation to be 7.74 into 10 power minus 19 joules. And this, if you are converting it into electron volts, you will divide this by 1.602 into 10 power minus 19 joules, and you will get this as 4.83 electron volt. And why we have converted into electron volt? Because the stopping potential, when you are going to multiply this with E, is what you are going to get equal to the work done by the stopping potential, right? So that work done by the stopping potential is equal to the kinetic energy. So 0.35 into E is going to be equal to the kinetic energy. So we have kinetic energy of the electron to be 0.35 electron volt, right? And now the work function, this is going to be the energy of the incident radiation minus the kinetic energy. So we get 4.83 electron volt minus 0.35 electron volt. And the answer for the work function for silver metal would be 4.48 electron volt. So I hope it is clear to you that the stopping potential, that is multiplied by E, that is the charge on electron, that is equal to the kinetic energy of the electron. So that is how we are utilizing this to get the kinetic energy of the electron. Now we've studied quite a lot about the electromagnetic radiations. We studied about the electromagnetic wave theory, giving us many phenomena of the radiations could be explained by the wave nature, and then we studied about the particle nature of the electromagnetic radiation. So assuming of the particle nature, the properties of the electromagnetic radiations like black body radiation, photoelectric effect, they are explained, while by the wave nature properties like diffraction and interference, they can be explained. So Einstein proposed a dual nature behavior for the electromagnetic radiations. And what did he say? He said that whenever radiation they interact with matter, it displays particle-like properties, while when it is propagating, then at that times it is going to have wave-like properties. And there are certain microscopic particles as well, like the electrons, which exhibit this dual character, right? So the electromagnetic radiations, they have both type of behavior, particle as well as wave. So I hope the whole of the photoelectric effect, the stopping potential and the numericals, they are all clear to you. In case you have any doubt, please do mail us at h2ochemistry@gmail.com. For now, that is all for this lecture. We would meet again for lecture 10 on the topic spectra in the course the atomic structure on the channel H2O. If you've liked the lecture, please do click on the like link and also do subscribe to our channel. Also do click on the bell icon so that you get a notification as and when we put up a new lecture for you, a new course for you. So bye for now. Have a nice day. Enjoy your studies. God bless you all.